All right, welcome to the complex plane and DeMoivre's theorem. So first we're going to start off with some definitions. We're going to be working with complex numbers during this lesson, and if you'll recall, a complex number is one that has a real part and an imaginary part. So z here, which is x plus yi, is our complex number. X represents the real part, and yi is the imaginary part. Okay, so z could be something like 2 plus 3i. So 2 is the real part and 3 is the imaginary part, where I is our imaginary unit. Now we've seen the need to introduce complex solutions before when we were solving equations. And remember, we couldn't find real solutions, so we would have to open up our field to include imaginary or complex numbers. So first definition here, let z equal x plus yi be a complex number, and the magnitude or modulus of z denoted by, it looks like absolute value bars, right? The modulus of z is defined as the distance from the origin to the point xy. So the modulus is the distance from the origin to that point. And it's defined to be the following, the square root of x squared plus y squared. So this is the modulus of z. Notice if z, the complex number, is x plus yi, then this distance is x, this distance here is y, and now I've made a right triangle, so it makes sense that in order to find the modulus of z, I would find the hypotenuse of that right triangle. We have another way to find the complex, the modulus of it, and it involves a complex conjugate. So z bar, that little bar on the top, is the complex conjugate of z. So for example, since z is 2 plus 3i, then that means z bar would be 2 minus 3i. And we have our conjugate pairs theorem that we studied before when we were finding complex solutions, which told us that complex solutions always come in conjugate pairs. You always have two at a time. So another way to compute the modulus of z is by taking the square root of the product of z and z bar. Okay, and then lastly, we can express these complex numbers in polar form as well. So if r is greater than or equal to 0, we do require r not be negative and theta has to be between 0 and 2 pi, then the complex number z equals x plus yi may be written in polar form as following. So I could write it, instead of x, I could replace it with r cosine theta, and instead of y, I could write r sine theta, and then I could factor out the r from both terms and then just have cosine theta plus I sine theta. So to help you understand why this is the case, let's draw another picture down here. But it's basically making a connection between polar coordinates and this complex plane. So here's my point, I'll call it z, which is x plus yi. So this height here is y. And this right here is the modulus of z, but that's r, right, when we're working in polar. Here's theta, here's x. So we know that x is equal to r cosine theta, y is equal to r sine theta, and since we had z equals x plus yi, I can write r cosine theta instead of x plus r sine theta instead of y, I. And then you can factor out that r, so you have cosine theta plus, and then you write the I in the front, sine theta. And then a lot of the times you'll see this abbreviated, z equals r. Since theta is going to be the same, you can just write cis theta. What does cis stand for? Cosine, I, sine, C-I-S. Okay? Saves you quite a few pen strokes, okay? You're gonna like it. Anyways, let's look at some examples here, just plotting and getting familiar with complex numbers. Okay, plot each complex number in the complex plane and write it in polar form. Express the argument, theta, in degrees, okay? So remember, theta, when you're writing your complex number in polar form, has to always be between 0 and 360 or 0, oh no degrees, 0 and 2 pi. Okay, and then if we need to round, let's round to 2 decimal places. Okay, so first things first, we have 2 plus rad 3i. So 2 is the real part, and rad 3 is the imaginary part. So when you graph it, the real axis is where the x-axis is. The imaginary axis is where the y-axis is. So this is your real axis, this is your imaginary axis. And this point, I'm going to go 2 units in the real direction, and then rad 3, which is about 1.7 in the y direction, or along the imaginary axis. So 2, 1.7, looks like it's about there. Okay, so there's my point. Now they want me to express this point in polar form, meaning I need to write it in the form z equals r cis theta. So I have to find 2 things. I need to figure out what this r is, and I need to know what theta is. Well, look, this height here is rad 3. This here is 2. So I can find r easily. R is going to equal the square root of x squared plus y squared. So that's going to be the square root of 2 squared plus 3. So that's rad 7. And then tangent of theta is equal to y over x. Just think back to how we did it in polar. So that's rad 3 over 2. So theta equals tan inverse of rad 3 over 2. No, that's not a nice one that we know from the unit circle. Don't let the rad 3 over 2 deceive you. So in your calculator, you can get that this is approximately 40.89 degrees. Okay, so if I were to write it in polar form, now I would say z is equal to rad 7 cis 40.89 degrees. Okay, if you don't like the cis, if it's bothering you and you want to write it all the way expanded, then that would be rad 7 cosine 40.89 plus I sine 40.89 degrees. All right, good. Example B, 4 minus 4i. So here we go. So here's the real axis, here's the imaginary axis. I have 4 minus 4i. So this is the real part. This is the imaginary part. So I'm going to come to 1, 2, 3, 4, and then down 1, 2, 3, 4. So here's the point. This is 4. This is negative 4. I need theta, I need r. Okay? Well, this is a nice isosceles right triangle. So I already know, okay, r is 4 rad 2. And theta is going to have a 45-degree reference angle, but remember, I can only give my angles between 0 and 360. So it's going to be 360 minus 45, which is 315. So that means I can write my complex number as z equals 4 rad 2 cis 315 degrees. Good. All right, now we're going to go the other way. So we have complex numbers in polar form, and we're asked to write them in rectangular form. So all you do is just compute whatever cosine of 5 pi over 6 and sine of 5 pi over 6 is. So this is going to be 2 cosine of 5 pi over 6 is negative rad 3 over 2 plus I times sine of 5 pi over 6 is a half. And then distribute the 2 and always put the real part first, even if it's negative. So we're going to have negative rad 3 plus I. Real part comes first, imaginary part comes second. Just like x comes first in an ordered pair and y comes second. Okay, that was pretty easy. Let's just do one more to make sure. So I have 3 times cosine of 210 plus I sine of 210. Okay, so this is going to be 3 times cosine of 210, that's in quadrant 3, so that's going to be negative rad 3 over 2 plus I times sine's also going to be negative there, negative 1/2. And then I'm going to distribute the 3, so I have negative 3 rad 3 over 2 minus 3/2 I. So put the I after the constant. Okay. Good. Now, let's see, why are we writing these complex numbers in polar form? Because of what's coming up next. So let Z1 equal R1 cosine theta 1 plus I sine theta 1, and then Z2 is going to be R2 cosine theta 2 plus I sine theta 2. These are two different complex numbers. Then, if I want to multiply them by each other, all I need to do is multiply R1 by R2, and then I still have cis, or cosine plus I sine, of the sum of their angles. Okay, you don't multiply the angles, you add them up. And then if Z2 is different from 0, then I can divide the complex numbers, and same thing, you just divide R1 by R2, and then you subtract their angles, theta 1 minus theta 2. So the complex number that's in the denominator, that's the one that gets subtracted. Just like negative exponents, right? Go in the denominator. Think of it that way. Okay, so for the following examples, we're going to find Z times W and Z divided by W, and then leave our answer in polar form. So we could leave it R cis theta, okay? We don't have to go back to rectangular. So let me just rewrite these so they're a little easier to work with. So Z is 1 times cis 120, and W is also 1 times cis 100. So Z times W is going to be 1 times 1 cis of 120 plus 100. 1 times 1 is 1, so I just have cis of 220. And I can leave it in polar form, so I don't have to figure out what cosine and sine of 220 are, which is good because they're not very nice. They're not from our unit circle. So, and then Z divided by W, we have 1 divided by 1, cis, and then you do theta from Z, so 120 minus theta from W, which is 100. So this is going to be 1, and then cis 20. Good. All right, let's move on to our next example. Example B, this time we're in radians, no big deal. I'm just going to identify R1 is 4, and theta 1 is 3 pi over 8. And then R2 is 2, and theta 2 is 9 pi over 16. Okay, good. So now let's take their product. So Z times W, that's going to be R1, R2, cis, theta 1 plus theta 2. So that's going to be 4 times 2, cis, 3 pi over 8 plus 9 pi over 16. So that's going to be 8 times cis. So 3 pi over 8, to get a common denominator, I'll multiply by 2. So that's going to be 6 pi over 16. So 6 pi plus 9 pi, that's 15 pi over 16. And then make sure that that angle is between 0 and 2 pi, which it is, so we're good. Otherwise, we'd have to fix it and give something coterminal. Okay, so that's Z times W. Now Z divided by W, that's going to be R1 over R2, cis 3 pi over 8 minus 9 pi over 16. So this is going to be 2 cis. Now 3 pi over 8 becomes 6 pi over 16. So 6 pi over 16 minus 9 pi over 16 is negative 3 pi over 16. And that's a no-no because remember, theta has to be between 0 and 2 pi. So what I'm going to do is add 2 pi. But 2 pi, if I'm getting a common denominator, is 32 pi over 16. So 32 pi and a negative 3 pi, my final answer is going to be 2 cis 29 pi over 16. Lovely. Okay. Let's do one more. This time, notice, so rude, they didn't give it to us in polar form already. So we have to do that first. So z is 1 minus I. So let's plot it. That usually helps. So the real part is 1. The imaginary part is negative 1. So here's z. Okay. If this is 1, that's negative 1. I already can tell R1 is going to be rad 2, right? And theta 1, that's going to be a pi over 4 reference angle. It's going to be 7 pi over 4 so that we end up in quadrant 4. Okay, now let's do the same thing for W. So W, the real part is 1. The imaginary part is negative rad 3. So here, my imaginary axis, here's the real axis. Ooh, that's too crooked. Okay, here we go. So here's 1. Here's negative rad 3. Here's where W is, okay? So what's this radius here? You could just do the Pythagorean theorem quickly in your head. Rad 3 squared plus 1 squared is 4. So R2 is going to be square root of 4, which is 2. And then what's theta 2? Well, this side here is negative rad 3, and this is 1. So it's a pi over 3 reference angle, but remember I have to make sure it terminates in quadrant 4. So theta 2 is 5 pi over 3. Okay, the worst is over. Now we can go ahead and compute the product and their quotient. So z times w is going to be r1 times r2 cis theta 1 plus theta 2. So r1 times r2, that's going to be 2 rad 2 cis 7 pi over 4 plus 5 pi over 3. Okay, 7 pi over 4 plus 5 pi over 3. We need a common denominator. We're going to show you a little slick way to multiply. It doesn't give you the least common denominator, but sometimes it'll just do the job so nice and quick. How can you resist? You go this diagonal product, so that's 21 pi, times this product, which is 20 pi. So 21 pi plus 20 pi over, and then you just multiply the denominators, 12. Sometimes you have to reduce after. That's the only reason this isn't like the most standard way to do it. But if you don't have to reduce, then you're done. So we have 2 rad 2 cis 41 pi over 12, okay? And then you have to ask yourself, is that within 0 and 2 pi? No, it's not, right? 2 pi is 24 pi over 12, and this is way bigger than that. So I have to subtract 24 pi over 12, because this answer is out of bounds, and I'm left with, that's a 12, that's a 12. So 41 minus 24 is going to give me 17. So we have 2 rad 2 cis 17 pi over 12. All right, that looks good. Now what about their quotient? Here we go. So z divided by w is going to be r1 rad 2 divided by 2 cis, and then we have 7 pi over 4 minus 5 pi over 3. So this time you can do the same trick from above. You're just going to change this to subtraction. So 21 pi minus 20 pi, that's just 1 pi over 12. So this one's easier. We have rad 2 over 2 cis pi over 12, and that's within 0 and 2 pi, so that one's done. So we can box it. Okay? Very nice. Now let's get on to the finale of the lesson, DeMoivre's theorem. Very exciting. So if z equals r cosine theta plus I sine theta is a complex number, then z raised to the nth power is equal to r raised to the nth power, and then you take the angle theta and you multiply it by n, okay? Where n is greater than or equal to 1, and it has to be a positive integer. So you're not going to raise it to a fraction like 1/2 or something like that. Okay, so here's some examples. Write each expression in the standard form a plus bi. So what we're going to do is use DeMoivre's theorem. I'm not going to actually sit there and raise this to the third power and expand it out the long way, right? I know this is asking me to take 3 cis 80 and cube it. So by DeMoivre's theorem, I know I can just take 3 and cube it, and then I'm going to have cis of 3 times the angle, okay? And so this is going to give me 27 cis 240. Now this time the directions say to write it in standard form a plus bi, not polar form. So I can't leave it like this. I have to expand it and switch it to rectangular. So this is 27 cosine 240 plus I sine 240. So we're going to have 27 cosine of 240 is going to be negative 1/2 plus I times sine of 240 is negative rad 3 over 2. So this is going to give us, once I distribute, oh, excuse me, that's a 27. Once I distribute that 27, we'll have negative 27 over 2 minus 27 rad 3 over 2i. Okay, good. Let's look at another example. This time I have rad 2 cis 5 pi over 6 to the 4th. So you take rad 2, you raise it to the 4th, and then you have cis 5 pi over 6 times 4. Okay, rad 2 to the 4th, you basically square rad 2 2 times in a row. So rad 2 squared is 2, and then squared again. Now it's 4. And then we have cis 5 pi over 6 times 4. That's going to be 20 pi over 6, which is 10 pi over 3. And that's bigger than 2 pi, right? 10 pi over 3. 2 pi would be 6 pi over 3. So let me subtract 6 pi over 3. And this is 4 cis 4 pi over 3. But remember, I can't leave my answer in polar form. I have to rewrite it in standard form. So I'm going to write 4 cosine 4 pi over 3 plus I sine 4 pi over 3. And then let's see here. So we're going to have 4 times cosine of 4 pi over 3. That's negative 1/2. And then sine of 4 pi over 3, negative rad 3 over 2 times I. And then distribute the 4, so we'll have negative 2 minus 2 rad 3i. Okay, one last one. So we have 1/2 cis 72 raised to the 5th power. So again, you just start off taking r, raise it to whatever n is, and then I'm going to have cis 72 times 5 degrees. So 1/2 to the 5th, that's 1 over 2 to the 5th, which is 32. And then cis 72 times 5 is 360. So this is going to be 1 over 32 cosine 360 plus I sine 360. Well, this one's fun because this is 1 over 32 cosine 360 is 1, sine of 360 is 0. So there's no imaginary part anymore. When I distribute the 1 over 32, I just get 1 over 32 times 1. So this is a completely real number. Okay, good. Now we can use DeMoivre's theorem sort of in reverse to find complex roots of a number. So what do we mean by that? So say W is your complex number and it equals R cosine theta naught plus I sine theta naught, and let n be greater than or equal to 2, an integer. As long as your complex number is not 0, there's n distinct complex roots of it, given by the following formula. So z sub k is the nth root of r times cosine of theta naught divided by n plus 2k pi divided by n, however many roots you're finding. So notice here, you take the nth root of r, you divide theta and 2 pi k by that n, and then k will start at 0 up until n minus 1. So it's going to give you all n roots. Okay, so you can have any complex number and say, I want to find its 10th roots. You can find all 10 of them. All right. If you think about it this way, like if you have only real numbers, then you have not as many options. Like there's 2 square roots of positive numbers when you're only talking about real numbers. But you could say, I want all the 4th roots of a number. Some are going to be real, some are going to be imaginary, like that. Okay, we'll work through 2 examples for you to see. And once you get a feel for the formula, just memorize it and then you'll be fine. So example 1, we're going to find all the complex roots and then leave your answer in polar form, thank goodness, with the argument in degrees. So they want the complex 4th roots of rad 3 minus I. So if they want the 4th roots, then that tells me n is equal to 4. And then here's my number w. So w is rad 3 minus I. First things first, I need it in polar form. Okay, so let's draw it out. Real part is positive rad 3. Imaginary part is negative I, so that's going to be negative 1. So it's over here. Okay. So that means r is equal to 2. And what's theta? Well, let's see here. Tangent of theta is going to be negative 1 over rad 3. So then theta is going to end up being a pi over 6 reference angle, since sine is going to be a half and cosine's rad 3 over 2. So that would be 330 degrees. Good. Okay. So that means I could write W as 2 cis 330. Okay. Now, if we're finding 4th roots, then that means I have Z0, Z1, Z2, Z3. Okay, you always start with 0 for the initial up until n minus 1. That's your last one. So let's use the formula here. So Z sub k, so k is going to be between 0, 1, 2, and 3. So Z sub k is going to be the 4th root, because we're finding 4th roots for this problem, of 2, 4th root of 2, and then you're going to have cis, you take that initial angle 330, you divide it by 4, plus, and then instead of 2k pi, I'm going to have 360 degrees k, and then divide that by 4. Okay, so let's clean this up first. So z sub k is the 4th root of 2 times cis 330 divided by 4, that's 82.5 degrees plus 90 degrees times k. Okay, so look here, here's k, here's k. K is going to go from 0 to 3, and that's why I'm going to get all of my 4th roots. Okay, so z sub 0, that's going to be the 4th root of 2 times cis of 82.5 degrees plus 0. So that one's done. Z sub 1 is going to be the 4th root of 2 times cis. Now, if I'm substituting in 1 for k, I'm going to add 90 to 82.5. And that's going to give me 172.5 degrees. So you just keep adding 90 to the angle. Z sub 2 is going to be the 4th root of 2 cis 262.5. And last one, z sub 3, I just keep adding 90 to the angle, is the 4th root of 2 cis 352.5 degrees. If you get carried away and you do too many, you're going to go out of bounds. You're going to go over 360. So here's all the 4th roots. What does it mean? Well, any of these numbers, so z0, if I raised it to the 4th, would give me the same thing as z1 raised to the fourth, which would give me the same thing as z2 raised to the fourth, or z3 raised to the fourth. And what would I get? I would get back w, rad 3 minus I. Okay, good. Let's do one more. This time let's do it in radians. Why not? We'll do this one in radians. So find the complex cube roots of -8. Well, notice -8 is a completely real number. So that means if I were to write it in standard form, it's the same as -8 plus 0i, right? Well, where would that be? That would be over here. On the negative x-axis, r is equal to 8, and theta would be pi. Okay, and if we want the cube roots, then that means n is equal to 3. So k is going to vary starting from 0 up until 2. 0, 1, and 2. Okay, so first let's write our number w in polar form. So w equals 8 cis pi, which means z sub k is going to be the cube root of 8 cis, and then you take that angle, divide it by n, so 3, plus 2 pi k over 3. And then I can clean this up a little bit. So this is going to be 2 cis pi over 3 plus 2 pi k, or 2 pi over 3 times k. Okay, so let's get going. So we'll do k equals 0, k equals 1, and k equals 2. So z sub 0 is going to be 2 cis just pi over 3, because k is 0 there. Z sub 1 is going to be 2 cis pi over 3 plus 2 pi over 3. So that's 2 cis pi. And then z2 is 2 cis pi over 3 plus 4 pi over 3, which is 2 cis 5 pi over 3. Okay, good. So these are all of the cube roots of -8. Now I want to point out something. One of these you already know. 2 cis pi, that's 2 times cosine of pi plus I sine of pi, right? And cosine of pi is -1, sine of pi is 0, so this is -2. And I'm sure if I asked you before watching this video, what is the cube root of -8, you would say -2. But the whole point of doing this process is that if you want cube roots, you should have 3 of them. So there's one real one and the other 2 are imaginary. Or if I wanted 4th roots, there should be 4 distinct ones, and I'm going to have to involve imaginary or complex values in order to get them all. Okay? So just practice, and I hope you enjoyed the lesson on DeMoivre's theorem.